In a previous video, we talked about Horner's method and how it made visible a bridge between what we called function value island and polynomial division island. And that bridge was something called the polynomial remainder theorem. And the polynomial remainder theorem just states that the remainder, when we divide a polynomial f by x minus p, where p is just some value, is equal to f of p. And a more specific version of that was the factor theorem that stated that x minus p divides evenly into f, in other words, gives the remainder of 0, if and only if f of p is equal to 0. And what we want to look at in this video is an extension of this characteristic here, namely that x minus p to the kth power is evenly divisible into f if and only if f of p is equal to 0 and f prime of p is equal to 0, etc., until we get to the k minus 1 derivative of f, evaluated at p, being equal to 0. And if we call this first f of p just the 0th derivative, and if we call f prime just the first derivative, then we can see that we're dealing with the numbers 0, 1, all the way to k minus 1, in other words, k derivatives. So if k derivatives, and again we're counting the function itself as the 0th derivatives, are equal to 0, if the first k derivatives are equal to 0, then the function is also divisible by x minus p to the kth power. In other words, if we had a function f that we divided by, let's say, x minus 1 4 times, and it divided evenly, that would be the case exactly in those cases when f of 1 is equal to 0 and f prime of 1 is equal to 0 and f double prime of 1 is equal to 0 and f triple prime of 1 is equal to 0. Just to make clear what our new theorem means. So now let's take a look at an example that we'll do with Horner's method. We have this polynomial function here, and we write in the coefficients, and a little bird whispers to me that this might be divisible by x minus 1. So I write in my 1 here, meaning I want to divide by x minus 1, and we do Horner's scheme here. We multiply and add and carry and etc. And what are we left with at the end? We're left with a 0, which means that x minus 1 divides evenly into f. So let's continue, see if it's divisible by x minus 1 again. We carry and multiply and add and multiply, etc. And again we see we're left with a 0, which means now that x minus 1 squared divides evenly into f. Let's do this again. Again we carry and multiply, etc. And again we have a remainder of 0, meaning this time that x minus 1 to the 3rd power is evenly divisible into f. We'll try that one more time. And again we get the answer of 0, which means finally that x minus 1 to the 4th power is divisible evenly into f. And if we go back and look at our new theorem here, we see that if that's the case, then this must also be the case. So let's check and see if this is the case. So this 0 here also tells us, this 0 at the end of the first line of the Horner scheme, right, also tells us that f of 1 is equal to 0. And this 0 told us, of course, that the remainder was equal to 0 when we divided by x minus 1 squared, but it also tells us that f prime of 1 is 0. And this 0 tells us that f double prime of 1 is 0. Now, strictly speaking, what it tells us is that f double prime of 1 divided by 2 factorial is 0. Right, but if we multiply both sides by 2 factorial, we end up with this anyway. And this last 0 just tells us that f triple prime of 1 is equal to 0. So we see that it worked. We started here, and we saw that that meant that this was indeed the case. Of course, we also said that it would work in the other direction, right? We said if and only if. So now imagine that we started here with looking at these blue numbers, or these blue circles, and seeing that f of 1 is 0 and f prime of 1 is 0, etc. Then of course it would be the case, if we then looked at the black numbers in the black boxes, that these zeros are still there. Horner makes it clear that these are actually the same thing. This just means the same thing as this. And Horner makes that very clear. Yet another thing you can do with this wonderful method.